You can't say y equals something is a vertical line, right? It fails the vertical line test in the worst way possible. And yet, certainly, x equals to 0, y free is a solution, which is an orthogonal trajectory to this set of circles, is it not? Geometrically, isn't that obvious? X identically equal to 0, y free. You know, this point, yeah? I mean, that's this guy right here. That's definitely an orthogonal trajectory from just geometric reasoning. But that's not in my solution, right? That's just because I divided by y. Well, it's because I divided by x. I don't know however you want to look at it. But to see that that's actually a solution, what I do is I take this and I think about going back to here directly, right? And I think about, okay, well, 2 times 0 plus the derivative of 0 plus, oh man, wait a minute. You guys tell me why it didn't work. That's not equal to 0. That's just 2y dy. But which differential equation did I just use? Is this the differential equation for the orthogonal trajectories? It is not. You must be aware of this confusion. This is the principal and most dangerous confusion in an orthogonal trajectories problem, is to confuse the differential equation for the given set of curves to the different differential equation which describes the orthogonal trajectories, right? The meaning of y is different in these two different equations, right? In the sense that this is the one I was supposed to plug it into, right? No, 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 no. And so with that, we don't have this to face. We face minus 2y, the differential of 0, plus 2 times 0, the differential of y. And that is 0 because you either have the derivative of the identically 0 function or you have the identically 0 function right there, right? And again, what I just wrote down in blue is to be truthful, a shorthand for maybe a parametric viewpoint where x and y are both thought of as functions of time or something. But anyway, any questions about this? If I gave you a differential equation or a family of curves, could you find the orthogonal trajectory? I hope you could. It's not that complicated. You just either need to flip it and put a minus or reverse and put a minus in one of them, but not both. If you put it on both, it's not good. It's just something else. So. All right. Let me look at some pictures with you guys. It's my next exam. What I have to do for the last 10 minutes of class here is heavily, well, either calculationally onerous or it's just something you want to look at. So either way, projector. Yeah. Wait a minute, 10 minutes. I thought we end at 1, right? This is funny to me. All right. All right, I'm going to come back to this physics derivation some other day, all right? This is part of a longer discussion, which I usually call energy analysis. So this is actually, this next page and a half here is the derivation of the energy analysis idea, which basically says that you can describe the motion of a physical particle in one dimension governed by a conservative force by just looking at like energy velocity plot. Well, a velocity position plot called the phase plane. We'll come back to that, okay? We just run through these just to give you a quick rundown of what these examples mean and how to think about them. This first example is based on the same trick that I just did to find the sine solution over there. If we have, a constant acceleration, in other words, a is equal to dv dt, well, we can change the acceleration to v dv dx. So that gives us this constant is v dv dx, which gives us that a dx is equal to v dv. I'm sorry, I forgot to warn you to bring your Dramamine today. Or is it just me who sees the screen going, is that just me? No? You guys are just so used to your screens vibrating that you've just accepted it as students. Really? So you guys are, ostensibly the next generation of the conservative intelligentsia, right? You guys got to learn to complain better. Anyway, I'm just saying, I don't know. Anyway, I'm kind of disappointed in the level of complaining with students sometimes. So you need to work harder at it. Anyway, so you integrate, separate, integrate, and lo and behold, the timeless equation from Physics 231, right? So the v dv dx trick, it derives it with calculus, is my point. The next example is a very popular example that you have seen in probably 3 other courses. I'm not going to talk about it. Exponential growth. Done. This is the discharging capacitor. We'll talk about that some other day when I have more time. I'm trying to focus here on the things I need the projector for. So here's an interesting problem. Find a family of curves which are increasing for y less than 2 and y greater than 2, but are decreasing whenever y is between minus 2 and 2. So basically what I say here is the function you're thinking about is this quadratic, like y plus 2, y minus 2, that has that behavior. It's positive. Yeah, it's positive beyond 2 either way, and between the intercepts for the quadratic, it's negative, right? So if you say dy dx equals to that quadratic in y, that's going to make y be increasing beyond. I'm drawing y. I'm making y be horizontal for the moment of the discussion, but for y beyond plus or minus 2, we have that quadratic in y positive. For y between minus 2 and 2, we have it negative. So if we set dy dx equal to that quadratic in y, we should have solutions which are increasing before and after minus 2 and y, and they're decreasing between 2 and minus 2 and y. And you could write a differential equation to bear out whatever kind of geometry you want, right? You go back to Calculus 1, you think about what you learned about what the derivative says about increasing and decreasing for functions in graphs or concavity, and you can write down a differential equation which should have solutions which capture that geometry, right? So it's kind of a neat idea if you think about building a model. You could use a differential equation to find lots of curves with a certain property that you want. In this case, this increasing, decreasing business I just said. So then I solved the differential equation, which is separation of variables. This time we have to do the, what's this? Remember that technique? Partial fractions, right? Partial fractions decomposition, integrate both sides, bunch of algebra. After some algebra, I get to that's my explicit solution. Now I even got a picture of these. Here's a picture using that p-plane tool I showed you, or yeah, I think it's p-plane. And you can see some solutions there. Just like I said, they're increasing below minus 2 and above 2, and between minus 2 and 2, they're decreasing just like that. It's kind of neat. Of course, there are 2 extraneous solutions here, plus or minus 2 identical. Y equal to 2 or y equal to minus 2 are the special solutions, which are, you could call them equilibrium solutions, let's say. That's the orthogonal trajectories problem we just went through, 2.57. Here's another one. Find the orthogonal trajectories of x squared minus y squared equals to 1. So what do? I take the differential. That gives me the differential equation which picks up this as a solution, right? 2x minus 2y dy dx. I decided to do dy dx equals to x over y this time. It gives you a chance to see the other idea. That's my f. Here's minus 1 over f, right? And then I solve by separating variables again. And out pops this, which then algebra gives me y equals k over x. Here's a picture of both. I think actually I've got more. I mean, technically x squared minus y squared equal to 1 is just one hyperbola. So that would be maybe, I don't know, x squared minus, I mean, what we're looking at here is not just x squared minus y squared equal to 1. We're looking at x squared minus y squared equals to a constant. As that constant varies, it gives you a family of hyperbolas which open with respect to either the x or y coordinate axes. In contrast, this k over x, these give us reciprocal functions, which are actually hyperbolas which are rotated and are opening with respect to the y equals x or y equals minus x lines. So these are the orthogonal trajectories. And the blue are the again, x squared minus y squared equal to a constant to be more honest, yeah. So my picture doesn't quite match this. If I just had this, that'd just be one curve, right? But anyway, but it's not surprising. Well, I mean, if I had a C here, right, then the calculation below would be just the same, right? If I had the whole family, if I had like x squared minus y squared equal to a constant, finding orthogonal trajectories for the family versus finding orthogonal trajectories for a given curve in the family, it's pretty much the same calculation. So. All right. You know, you can solve problems with friction now. Suppose the force of friction on a speeding car is given by minus bv squared, right? If the car has mass m and initial speed v naught, and initial position x naught, find the velocity and position as a function of time as the car glides to a stop, all right? We're going to assume that the net force is the friction force since the normal force and gravity force cancel. So what we're looking at is ma equals to minus bv squared, right? But I use what did I do here? Oh, I just did it. Okay, so then separate. I get dv over v squared is minus bt over m. And then integrate. Minus 1 over v is minus btm plus, I don't know how you guys can stand it. Wow. Goodness. How can you guys keep looking at that? It's okay for you? It happens in every class? Good night. All right, anyway. So anyway, solving for v gives me this. What happens as time goes to infinity? As time goes to infinity, the velocity goes to 0, right? Because that gets really, 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 really big. So 1 over something, you know, that kills it. It goes to 0 eventually. On the other hand, we can integrate the velocity to find position, right? Integrate velocity, so dv dt is equal to, dx dt is equal to v, which gives me that x is equal to the integral of that, which is this. And so there's the position as a function of time, right? What happens as time goes to infinity there? Ooh, look at that. As time goes to infinity, we get log of infinity, which is infinity. So this is a funny thing, right? The position is unbounded, right? Even though the velocity is going to 0. So it's just, the position is getting really, 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 really big, but it's doing it slower and slower and slower and slower, but not so slow that it ever stops. That's calculus. We can also talk about Newton's law of cooling and a few other things, but I'll save those for another day, guys. Have a good day. Good day to you. No? Oh, okay.